Hi everyone, welcome to GemChem. Now today's video is on tautomerism, and in part 1 of tautomerism we are going to deal with Keto Enol Tautomerism in more details. So here we begin the topic of tautomerism. Already many videos are uploaded in channel. You can watch it. I will give the link in the description box as well as the I button present above this video. And if you are new to GemChem, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. So, the term tautomerism comes from a formation or a type of isomerism where we generally see that one atom migrates to another position and there is net change in the structure but no change in the formula. So, we can state it as structural isomerism where a single compound exists in two or more interconvertible structural forms which are known as tautomers. Generally, we see that proton migrates, but when we will go further into the details of this topic, we are going to see some other group migrations also. So this dynamic equilibrium is established generally by rapid reversible migration of an atom, usually a hydrogen atom, and the simultaneous shifting of a double bond within the molecule. So today we are going to deal with Keto Enol Tautomerism in more details. So here we can see that there is a shifting of proton. It is a proton that shifts from one atom to another molecule. Formation changes due to this proton shift. So very common form of tautomerism is this one, where you can see that this proton gives up its electron to form the double bond, and this oxygen takes up the hydrogen present here to form the enol. So here this is the keto, and this double bond including with the OH group gives your enol. In from alkene provides N, and phenol or alcohol gives you ol form, that is enol form. So why this equilibrium shifting occurs, or why do we see that generally in most cases the equilibrium lies to the left, that is why keto form is stabilized. So this can be answered with the help of examination of the bond energies which are present in both keto form as well as eno form. So in this case we are concerned with this carbon-hydrogen bond, this carbon-carbon single bond, and carbon double bond oxygen. And for the enol form we are dealing with carbon double bond carbon, carbon oxygen bond, as well as the oxygen hydrogen bond. So if we look into the bond energies in keto form as well as enol form and find out the total, we are going to see that there is a difference of 12 kilocalorie per mole within the bond energies of keto form and enol form. As a result of which we can conclude that this keto form is thermodynamically more stable than your enol form. So this is the reason why we see the major portion of these particular molecules in the keto version. Now, while studying Keto Enol Tautomerism, we are going to find out more details that how the structures in the different environmental conditions in the medium, or more appropriately reaction medium, changes the enol content for a particular tautomerism. So first example, when we look into, we observe that here when you take aldehyde, that is more appropriately acetaldehyde, and when you take acetone, the acetaldehyde has an enol content which is much negligibly small, whereas when we consider for the acetone we see that there is appreciable or very little 1.5 into 10 to the power minus 4 percentage of your enol content. So why this is so? It is found that when we are talking about this particular acetaldehyde, the interaction between the orbital present in the carbon as well as the orbital present in the oxygen is much significant, as a result of which this structure is more stabilized than this one. Whereas when we consider the same interaction in case of this carbon double bond oxygen, due to the presence of these alkyl groups, the orbitals are unable to properly orient themselves. As a result, due to this lack of proper matching, there is minimization of the stability of the structure and we get enol content. So when we look into the interaction, we see that the high bond energy present in the carbon double bond oxygen in acetaldehyde is due to the following interactions between the pp orbitals of carbon and oxygen. But such type of stable interaction is minimized in case of ketone due to the lack of proper matching. And this can also be proved when we dissolve acetaldehyde as well as this acetone in D2O. We see that in case of acetaldehyde, the enol form is present, but the exchange of the hydrogen with the deuterium is very much slow. Whereas when we consider for acetone, we generally observe that the exchange rate is much rapid, which shows that no such interaction as that of acetaldehyde exists in case of ketone or acetone. So from here we can conclude that aldehydes generally have lower enol content than your ketones. Next, if we see this example, where you can see that we have taken 2 aldehyde only, and the difference is that in this carbon, that is the carbon just after your carbon double bond oxygen, this carbon is known as alpha carbon. So this carbon as well as this carbon has different alkyl groups attached. In this case you have a ethyl group attached, and in this case you have 2 methyl groups attached. And this is the only point of difference between these two. And we can see that when only one alkyl group is present in the alpha carbon, and here 2 alpha carbon groups of alkyl are present here, the enol content have increased significantly, and this is only due to the presence of hyperconjugated structures. When you see here, in this case you can see that alpha carbon along with the beta carbon has 2 hyperconjugative hydrogens present, whereas in this case we have 6 hyperconjugative structures possible. As a result, due to the hyperconjugated stabilization of the enol form, the enol content in this case is much more. So we can conclude that with increase in number of alkyl groups on the alpha carbon of a carbonyl compound, the enol content increases. Now if we look into another example where we see that an aldehyde is being provided in both cases, but the alpha carbon has phenyl group replaced in case of alkyl groups, the enol content has increased significantly than the previous cases. So here we can see the one which was 1.4 into 10 to the power minus 2%, now it is 9.1. So from here we can easily understand that there is something involved with this phenyl group. So once it is in enol form, you can see here the oxygen lone pair can easily be given up. As a result, this bond can come here and this bond opens up. So this indicates the resonance stabilization. So from here we can conclude that when we introduce aryl group on the alpha carbon of the carbonyl compound, the enol content increases. So if we look into the resonance stabilization, so you can see here that once you continue with the resonance, there are so many structures obtained. Similarly, this is shown for this ring, but this particular resonance can occur also with these rings. So many resonance structure provides stabilization to the enol form. As a result, we can conclude that resonance stabilization of enol form makes the amount of enol content more. This was for aldehyde. If you take similarly pH CH2COCH3 and CH3CH2COCH3, then also enol content of pH CH2COCH3 will be higher than CH3CH2COCH3. Now look into this example more carefully. From here you can see that this is acetone. Now along with acetone we have introduced another ketone here. Similarly here also we have ketone, but this particular portion we have a ester group and here we have only a keto group. So from here we can understand that on introducing another carbonyl group in alpha carbon of the compound, the enol content drastically increases. And if you see the difference between these two, it is too much. So what is the reason for this particular enol content to be so much extra stabilized. The two reasons which are involved is, see here, the presence of hydrogen and oxygen can result in intramolecular hydrogen bonding in these two cases. Similarly, there is an enhanced conjugation present in between. Now, when we talk about conjugation, then these two has only this part different, as a result of which the enol content amount also gets changed, because the type of conjugation in these two are also different. So when you observe here you can see that the conjugation takes place between this OH, O, C and this double bond, right? But when we observe this part also, here this oxygen can give up electron. As a result, this can open up. Similarly, this double bond can come here and the double bond oxygen can open up. So in the two directions we have resonance occurring. But in this case, only unidirectional, and the resonance is occurring throughout in a one particular chain. So here we can see that there is a presence of cross conjugation. As a result, stability due to cross conjugation is not more than, in this case, which is extended conjugation. As a result, enol content for ethyl acetoacetate is lesser than enol content of acetyl acetone. So these were the four topics of discussions where we have seen that what are the effects of structure on the position of equilibrium in keto enol tautomerism. More appropriately, we have observed a difference of enol content between aldehyde and ketone. What happens when alkyl group number increases in the alpha carbon? What happens when you introduce aryl group in the alpha carbon? And lastly, we have seen that what happens when we introduce carbonyl group in the alpha carbon. In the next video also, we are going to see more effects of structures on the position of the equilibrium. Here, today we end the video. Hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment.